For centuries, we've relied on classical computers to solve problems and process information. These machines have been the backbone of our technological advancements, enabling everything from simple calculations to complex simulations. These machines, while powerful, are limited by the laws of classical physics. They operate within the constraints of binary logic, where every piece of data is processed as either a 0 or a 1. They store information as bits, which can be either a 0 or a 1. This binary system has served us well, but it also imposes significant limitations on what classical computers can achieve. But what if we could harness the strangeness of quantum mechanics to build a fundamentally different kind of computer? A computer that operates on principles that defy our everyday understanding of reality. Welcome to the world of quantum computing. This new frontier in technology promises to unlock capabilities that were previously thought to be impossible. Quantum computers are not meant to replace classical computers. Instead, they are designed to complement them, offering solutions to problems that classical computers struggle with. Instead, they are a new tool with the potential to revolutionize fields like medicine, materials science, and artificial intelligence. Imagine the possibilities, from designing new drugs to creating materials with properties we've never seen before. Imagine simulating complex molecules to design life-saving drugs. This could lead to breakthroughs in treatments for diseases that are currently incurable, or optimizing algorithms that could break today's encryption. This has profound implications for cybersecurity, potentially making our data both more secure and more vulnerable. These are just a few of the exciting possibilities that quantum computing offers. The potential applications are vast and varied, limited only by our imagination and ingenuity. At the heart of a quantum computer lies the qubit. This is the fundamental unit of quantum information. Unlike classical bits, qubits can exist in a superposition, a mind-bending concept where they are both 0 and 1 at the same time. This allows quantum computers to process a massive amount of information simultaneously. This unique property allows quantum computers to explore many possibilities simultaneously, giving them a massive advantage for specific problems. Problems that would take classical computers millennia to solve could be tackled in mere seconds. Join us as we delve deeper into the fascinating world of quantum computing. We'll explore the science behind it, the challenges we face, and the incredible potential it holds. We'll explore the principles behind this revolutionary technology and the potential it holds for the future. The journey into quantum computing is just beginning, and the possibilities are endless. In the quantum realm, things work a bit differently. Instead of bits, we have qubits. Qubits are like the superheroes of the computing world. They can be a 0, a 1, or both at the same time. This mind-boggling ability is called superposition. Think of a coin spinning in the air. It's not heads or tails until it lands. Similarly, a qubit in superposition is a blend of 0 and 1 until it's measured. This unique characteristic of qubits allows quantum computers to explore many possibilities simultaneously. Imagine searching through a maze, and instead of taking one path at a time, you could explore all paths concurrently. That's the power of superposition at play. This ability to explore multiple possibilities at once is what gives quantum computers the potential to outperform classical computers for certain tasks. It's like having a massive parallel processing unit that can tackle problems in a completely new way. Superposition is a fundamental concept in quantum mechanics that distinguishes it from classical physics. To understand it, let's visualize a qubit state as an arrow spinning on a sphere. The north pole of the sphere represents the classical state 0, while the south pole represents the state 1. In superposition, the arrow points to a point on the sphere that's not directly at either pole. This point represents a combination of both 0 and 1, where the qubit exists in both states simultaneously. The exact position of the arrow on the sphere determines the probability of measuring the qubit as a 0 or a 1. If the arrow is closer to the North Pole, there's a higher probability of measuring a 0, and vice versa. Superposition allows quantum computers to explore a vast space of possibilities simultaneously. With each additional qubit, the number of possible states the system can represent grows exponentially. This massive computational space is what gives quantum computers their potential to solve problems that are intractable for classical computers. Section 4. Entanglement, the spooky connection. Entanglement is another bizarre phenomenon in quantum mechanics that plays a crucial role in quantum computing. It occurs when two or more qubits become correlated, even when separated by vast distances. Imagine two coins flipping and landing on the same side, no matter how far apart they are. That's the essence of entanglement. When two qubits are entangled, their fates are intertwined. Measuring the state of one qubit instantaneously determines the state of the other, regardless of the distance between them. This spooky action at a distance, as Einstein called it, is a fundamental difference between classical and quantum mechanics. Entanglement enables quantum computers to perform operations on multiple qubits simultaneously. This interconnectedness allows for a speed-up in computation that is impossible to achieve with classical computers. It's like having a network of computers that can instantly share information and coordinate their efforts, leading to a significant boost in processing power. Section 5. Quantum gates, the building blocks of algorithms. In this section, we will delve into the fundamental components that make quantum computing possible. Just like classical computers use logic gates and Oregon NOT to manipulate bits, these gates form the basis of classical computation, allowing us to perform a variety of logical operations. Quantum computers use quantum gates to manipulate qubits. These qubits, unlike classical bits, can exist in multiple states simultaneously, thanks to the principles of quantum mechanics. These gates are mathematical operations that transform the state of a qubit or a group of entangled qubits. They are the essential tools that enable quantum computers to perform complex calculations. Single qubit gates act on one qubit at a time, rotating the qubit state on the Bloch sphere. This rotation can be visualized as moving the qubit state around the surface of the sphere. For example, the Hadamard gate puts a qubit into superposition, creating a state where the qubit can be both 0 and 1 simultaneously. This is a key feature that gives quantum computers their power, while the Pauli X gate flips a qubit from 0 to 1 or vice versa. This operation is akin to the classical NOT gate, but operates within the quantum realm. Two qubit gates, like the controlled NOT gate, C0, operate on two entangled qubits. Entanglement is a unique quantum phenomenon where the state of one qubit is directly related to the state of another, no matter the distance between them. The C0 gate flips the target qubit only if the control qubit is in the state 1. This conditional operation is crucial for quantum error correction and complex quantum algorithms. These gates are crucial for creating and manipulating entanglement between qubits. Entanglement is what allows quantum computers to solve problems that are intractable for classical computers. The Solovay-Kitaev theorem, a fundamental result in quantum computing, states that any quantum gate can be approximated to arbitrary accuracy using a finite set of universal quantum gates. This theorem underpins the feasibility of building practical quantum computers. This means we can build any quantum algorithm we desire using a relatively small set of building blocks. These universal gates are the foundation upon which we can construct complex quantum circuits, enabling groundbreaking advancements in fields like cryptography, material science, and beyond. Section 6. Quantum algorithms, speeding up the impossible. In this section, we delve into the fascinating world of quantum algorithms and how they are revolutionizing computation. Quantum algorithms are specifically designed to leverage the unique properties of qubits and quantum phenomena like superposition and entanglement. These properties allow quantum computers to perform complex calculations at unprecedented speeds. These algorithms can solve certain problems exponentially faster than their classical counterparts. This speed-up is not just incremental, it's transformative, enabling solutions to problems that were previously deemed unsolvable within a practical time frame. One such algorithm is Grover's algorithm, which offers a quadratic speed-up for searching unsorted databases. This means that tasks which would take classical computers years to complete can be done in mere seconds with a quantum computer. Imagine searching for a specific name in a phone book. In a classical scenario, this would be a tedious and time-consuming process. Classically, you'd have to look through each entry one by one, which could take a considerable amount of time, especially if the phone book is large. Grover's algorithm allows you to search the entire phone book simultaneously, finding the desired name much faster. This simultaneous search capability is a game changer in data retrieval and processing. Shor's algorithm, another groundbreaking quantum algorithm, can factor large numbers exponentially faster than any known classical algorithm. This capability is crucial for fields that rely on complex mathematical computations. Factoring large numbers is a computationally difficult problem that forms the basis of many modern encryption schemes. The security of our digital communications relies heavily on the difficulty of this task. Shor's algorithm's ability to crack these codes has significant implications for cryptography and cybersecurity. It challenges the very foundation of our current encryption methods, necessitating the development of new quantum-resistant algorithms. These are just a few examples of the power of quantum algorithms. The potential applications are vast and varied, spanning industries from pharmaceuticals to finance. As research progresses, we can expect even more powerful algorithms to emerge, unlocking solutions to problems that were once considered impossible to solve. The future of quantum computing holds promise for unprecedented advancements in technology and science.